So real quick, I'm going to go through the last three problems for the vectors. The first two are very straightforward. So we have this problem, and this problem. And they all have the same plane flying at altitude, so it's at a cruising speed and it's flying horizontally with respect to the ground at 200 kilometers per hour, and it encounters some sort of wind going 20 kilometers an hour. So with the plane flying at altitude and it encounters a headwind at 20 kilometers an hour, the headwind blows the plane from the front. So if we have a plane like this, here's our plane, and it's flying this way and it encounters a headwind from the front, that's going to slow down the plane. So this would be like, actually, I'm going to start with this one because this one is a little easier. So we have a plane flying forward at 200 kilometers an hour in this one, and it encounters a tailwind. So the tailwind pushes it from behind at 20 kilometers an hour. This is a bit like being in a lazy river and then swimming along with it. So if you're in a lazy river, you just get carried along with the river. So at a lot of water parks, they'll have some sort of lazy river where you get in an inner tube and you just float around with the current, and the water pushes you around at a constant speed. If you instead get out of the inner tube, and not all water parks like you to do this, but if you get out of the inner tube and you swim along with the current, you're going to go faster than the people who are just floating with the current. So this is like this situation here. We have 20 kilometer an hour tailwind and the airplane is already going at 200 kilometers an hour. So the plane goes faster than somebody just observing on the ground. So they see the plane go 220 kilometers per hour. If you wanted to solve this with grid paper or a protractor, you're just adding the vectors together, one after the other. These are both velocities, so we can just add them mathematically. In this situation with the headwind, that means the wind is blowing against the plane from the front. And with our lazy river example, that would be like swimming in the lazy river, getting out of the inner tube and trying to swim against the lazy river, and you're not going to swim as fast, and you might not move at all. So in this situation, the plane is not flying as fast. It's 180 kilometers per hour, which is 200 minus 20. And it makes sense again that it's minus 20 because the direction of the wind is against the direction of the plane. So anytime we have something going in opposite directions, we have negative numbers in physics. These are going in the same direction, so they get added together. So what about the crosswind? That one's the trickier one. So in this case, I'm going to draw a top-down picture. So we have, and it says, if the plane is flying south. So let's draw the plane flying south. There's the tail. So the plane is flying south at 200 kilometers per hour. But then it encounters a crosswind blowing it to the side at 20 kilometers per hour. So in the plane, instead of having the plane go straight this way, the plane will go diagonally, even if the plane goes at it is pointed straight down. So if this is the plane, because it's getting blown by the wind, it winds up going that way. So, since it's going this way, what will this velocity be? Just by drawing the picture, you should be able to see what kind of thing we've got going on here. And keep in mind, this plane is not falling, right? So even though it's going south, it's not falling. And it's also not going to, we're not going to need acceleration for this problem. Just like the plane wasn't accelerating for the first two problems, it's still not accelerating over here. But this looks like a right triangle. So to find how fast the plane is going with respect to somebody on the ground, it's still a squared plus b squared equals c squared, or c equals the square root of a squared plus b squared. So and we plug that into the calculator. And because 200 is so much bigger than 20, our answer won't be very much bigger than 200. So it's still fairly close to 200, but let's round that up. So 201 kilometers per hour is the magnitude. But notice in these two questions it says speed, which means we don't need the direction. In this question it says velocity, which means we do need some sort of direction. If you're in K physics, in one of my K physics classes, direction has to be an angle. If you're in my on-level class, you need to just state some general direction like south, east, southwest. It doesn't say on this one which direction the wind is blowing, so southeast or southwest would be fine. On a quiz or a test, it'll be more specific. But we can at least figure out the angle for K physics. And like I did with the first problem, anytime we find an angle, I like to use inverse tangent of the opposite side divided by the adjacent side. Now, I already marked out the angle that I want to use. So I want to, from here, I want to use this is our opposite side, and this is our adjacent side. So we get the inverse tangent of the opposite side is 20, the adjacent side is 200. And because 200 is so much bigger than 20, this should be a fairly small angle. Check the mode, just in case, especially if your calculator doesn't show it on the very front screen. Make sure you're in degree mode. So we have inverse tangent of 20 divided by 200. So our angle is 5.71 degrees from south. Again, this one specifically didn't say whether the wind was blowing towards the west or towards the east. So 51.7 degrees from south is about all that we can get for this one. For this next part, if the plane is trying to fly 600 kilometers south, just like in all parts of physics, our variables must match. So and that can mean a couple different things. So if we're adding vectors, the vectors have to be the same kind of vector. If we're solving for a separate kind of variable, they must match in the way that we're measuring the problem and calculating the problem. In this case, we are taking a distance directly south, which means we need to use a velocity that is directly south. So delta x equals velocity times time. We know we've gone 600 kilometers, so we need to use the directly south. Hours. So the amount of time it takes is 3 hours. And then if the plane doesn't correct for the crosswind, and by correcting for the crosswind, that means it flies into the wind a little bit, so that instead of being pushed sideways, it winds up, as it's flying this way, it's always pushed back, so it goes straight down. If it doesn't correct for the crosswind, that means it gets pushed this way. How far off course will the plane be in the amount of time of part A? So by the time it gets here, how far this way will it be? That's the same equation. And now instead of plugging in for delta x, we are solving for delta x. So we know it is going 20 kilometers an hour sideways. We know it takes 3 hours for it to get where it's going without the wind. So if it doesn't correct, if it flies straight down and gets pushed by the wind rather than trying to fly into the wind and go straight down, it will be 60 kilometers off course.